Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering BBD ITM Lucknow. Today we will take up course KCE 064 Foundation Engineering, and today we will take up lecture 37, in which we will cover design of reinforced earth part 2. References that I have taken: Dr. B.C. Punamia, Soil Mechanics and Foundation; V.N.S. Murthy, Soil Mechanics and Foundation Engineering; Alam Singh, Soil Mechanics and Foundation Engineering; Naptel, and some material have been taken from internet. Contents that we cover here is design consolidation and design of a numerical. So, this is a continuation of lecture 36, in which we will cover after we have already covered in lecture 36. So, here the next is check for the internal stability. The internal stability will be checked for static and seismic separately. In static cases, first of all we have to compute the earth pressure coefficient KAW and KAW dash using the equation given here. It is already given here. It is K is equal to cos square phi 2 divided by cos delta in 1 plus sine phi 2 plus delta 2 sine phi 2 divided by cos delta 2 to the power 1 by 2 the whole square. So, in this way we can calculate the earth pressure coefficient KAW, and in same way we can calculate the coefficient of active earth pressure for the static case for the soil. So, here it is obtained by the using delta by 2 in the above equation. Then we can find out the soil, the coefficient of active earth pressure below the soil of water level. Using wall field properties like C1, phi 1, gamma S1 and KAW dash, that is the earth pressure coefficient value below the water table, will be obtained by using delta 2 is equal to delta 2 by 2 in the above equation. The tensor failure Ti, that will be the KAW and KAW dash and sigma Vi and Sz for the grid type reinforcement. For Ti, KAW and KAW dash sigma Vi Sz Sx for the strip type of the reinforcement, where Sx is the horizontal spacing between the strip, sigma Vi is the vertical stress which will be taken as the sum of the vertical stresses as given in for Hi less than or equal to H minus Sw. Sigma Vi is equal to gamma 1 Hi plus Q plus Mi 6 by L square. For Hi more than H minus Sw, so Vi will be equal to gamma H minus Sw plus gamma B1 into Hi minus H minus Sw plus M2 6 by L square. So in this way we can calculate the value sigma vi, and sigma vi is equal to v 1 divided by di into 1 plus sigma 6 e dash divided by di. So we can calculate the various parameters in this way. Tension in the reinforcement computed will be added to Ti above, and for the satisfactory design, that will be Ti should be more than TRT. For this condition is not satisfied, then the redo this step by reducing the spacing between the reinforcement. Next is pull out failure. We have to compute A3, A9, A10, A11 and A12 using the different equation, and after this compute beta C, then compute T max. If n is the number of layer of reinforcement, then compute Ti as a T max divided by n. So then compute anchorage length LIP, then obtain the required length of the reinforcement, then the length should be less than the assumed length, otherwise adopt the computed length. Then we consider seismic case. In the seismic case, we have to compute this thing in the similar fashion. Compute the following as pressure coefficient, that is KDW and KADW dash using the wall fill property delta 2 by 2 and phi as tan inverse 1 gamma S1 divided by gamma S1 minus 1 alpha H divided by 1 plus minus alpha V. So we can compute this one. Then the tension failure, we can calculate this one. Ti is equal to, this is given, KADW or KADW dash sigma VI SZ for the grid type of reinforcement, and Ti KAW or KAW dash sigma VI SZ SX for the strip type of reinforcement. So we can compute this one. Ti is computed by the equation will be added to this sum. So in this way we can go for the satisfactory that Ti is greater than 1.25 RT. If the condition is not satisfied, in this case redo this step by reducing spacing between the reinforcement. Then come to the pull out failure. Compute again A3, A4, A5, A6, A7, A8, A9, A10, A11 and A12 using different equation. Depending on this, for the particular value of Z, beta C is obtained, and finally compute T max. If n is the number of layer of reinforcement intersected by the failure waves passing a point at a depth Z will be T max by n, and Z is the depth. If the maximum tension taken by an individual reinforcement is considered as the T max AB, then T max AB should be more than RT. The value of anchorage length and the length of reinforcement may be obtained by the equation obtain the required length of reinforcement. So based on this consideration, we will consider a illustrative example in which we will cover entire things. So here we have a design a suitable layout of tensor SR2 grid reinforcement for 6-meter height vertical soil wall. The property of wall fill and backfill are given here, that are already given here, and the backfill data or parameters are given here. Then the water table is 2 meter above the base of the wall. The wall is situated in the seismic region. Alpha H is equal to 0.1 and alpha V is equal to 0.05. The backfill and the wall has surcharge of 8 kilonewton per meter square. The safe design strength SR2 grid is 16.5 kilonewton per meter. The allowable soil pressure is 200 kilonewton per meter square. So this is the question, and this question has been taken from the books of Swami. So here we can go for design. This is the, we have to calculate whatever we have discussed already, we cover in this numerical. So first of all, earth pressure coefficient due to backfill we have to consider. Here the most important part is delta 2 is equal to 2/3 of the internal friction, that is 5 to 2/3 by 5 is equal to 2/3 into 38, that is 25.34 degree. So by the equation we can solve the, we can calculate the value of coefficient of earth pressure active. Here psi is given, so we can calculate the psi, the tan to the -1, alpha is divided by 1 plus minus alpha v. So we can calculate the 6 degree with a minus sign. So now come to the considering the AD, KAD. Again, by putting this the value here, we can calculate the value 0.285. So with the minus alpha v, we can calculate again KAD, and that will come 0.264. So we can adopt higher one. So this is the higher value, 0.285. 285 value we have taken. So now below water level. Now come to the below water level. So again here delta by 2 will be taken as considered for this one, and so that will come 12.67 degrees Celsius. Again we will consider the coefficient of earth pressure in a static state, a static case. So putting the entire value we have already have, and that will come 0.221. So and here psi will be equal to 11.9 degree after putting the value in the formula. So now considering the seismic case, then plus alpha v, we can calculate the k dash AD, by which we can get 0.31, 0.351. Again considering minus alpha v, then we can putting the values of each parameter, finally we will get 0.331. So adopt k dash, the maximum of this one. So this is the maximum one. So we will consider, or we will adopt in this design 0.351. So now come to the total earth pressure and the moment. We have to calculate it. So again we have to calculate this one. Earth pressure at the moment, here is the P A gamma. We put the value of entire parameters we have already have, and and that will finally come to the 67.49 kilonewton per meter. So now considering PAQ, and by this formula we can put the value of each parameter, and finally we can calculate it. That will come to 10.48 kilonewton per meter. So like this way we can calculate the PAC, and putting the parameter value in this equation we will get 11.21 kilonewton per meter. Again PAW we can calculate, putting the value of parameters we will find 20.20 kilonewton per meter. Likewise we can calculate the PTST by adding this all, this one plus this one minus this one plus this one, so that will come 86.76 kilonewton per meter. Now we have to calculate the moment. So calculating the moment we have to go for AMAY, putting the value of each parameters in this equation we will get the value, that is 138.93 kilonewton meter per meter. So we can calculate MAQ, MAC in this fashion. So we will get this one, and again we will get this one. Again MAW, we putting the value of each parameter we will get the 13.33 kilonewton meter per meter. Now MTST, the summation of all with the numerical value, that will come the 150.01 kilonewton meter per meter. So now considering the dynamic increment, we have to go for this one. So again we will calculate the value of each, that is P A gamma I, P A Q I, P A gamma I, and getting the different value. Again MQI, and after that we will get this one. So now we have to calculate the forces and the moment related to wall and surcharges. Is it? So let the length of reinforcement is 5 meter. So W W W dash W M W M W dash Q and MQ we will calculate after putting the value of each parameter in this equation. And so finally horizontal seismic force on the wall will be calculated by WW dash into alpha n, that will be equal to 59 kilonewton per meter. Likewise on the vertical seismic forces on the wall, we will go after putting the value of each parameter in the equation, we will get this 173.0 kilonewton meter per meter, and the value of MSW V is equal to plus minus alpha V into W AV L by 2. So finally we will get 73.75 kilonewton meter per meter. Again we will consider vertical seismic forces on the surcharge acting on the wall. So we can calculate the this is putting the value of each parameter, we will get 2 kilonewton per meter, and the moment will be MSQH, we will get 24.24 kilonewton meter per meter, and MSQV we will get 5.0 kilonewton meter per meter. So because this example has been solved taking the earth pressure corresponding to plus alpha V case, further design is illustrated only for this case. Similarly, the design may be carried out for minus alpha V independently. So now we can go for checking. First is external checking. The first one is sliding. We have to check against the sliding, and the first we will consider a static case. Putting the value in the equation, we will get this value which is more than 2, so it is as safe. In seismic case, putting the value of each parameter and finally calculated, that could be 1.57, and that is more than 1.5, so it is a SF. Now we go for checking the stability against the overturning. In static cases, again here we calculate the S0 by this equation. Putting this value, we will get 8.83, which is more than 2, hence it is SF. Considering the seismic condition, again calculating the value of each parameter after putting the value of each parameter in the equation, we will get 3.42, that is more than 1.5, hence it is a safe. Now go for tilting and bearing failure. So first we will consider a static case in which alpha maximum we can calculate and alpha minimum we can calculate. Finally we get this one. So for the seismic case, we have to add each one of this. So finally it will come 410 kilonewton meter per meter. So alpha maximum we will get after putting the value of each parameter in this equation, we will get 13.8 kilonewton per meter square, which is more than 0, hence it is a safe. So internal stability, we can calculate the value of in the same fashion. We will get the value of this one. Again, calculating this value 0.265. Below water level, we can calculate the different earth pressure parameters by putting the value of each parameter in the equation. We will finally get 0.309. In a static case, we can see this is the static conditions. So we can calculate this one by putting the value of different parameters in the equation. For the safe design, that should be 16.5. It is given in the question. So it is 16.5 kilonewton per meter. In the limiting case, that should be RT. So after calculating this value, and it will give the H1 value is given here and SZ value is given here. So HI should be more than H minus SW. So again we calculate the MAY or other parameter by putting the value of each parameter that we already have in the equation, and then we will find out. Again, we can see here we have already calculated this one. They are the different equation that we have, and putting the value of each parameter in the equation, we will get the different parameters. So again we can see here for the satisfactory action that should be 16.5. So here 16.5. For H1 it is given here 5 and 6, and SZ 3.08 and 4.47. So in this way the value is 4.0, that is in the seismic case. So we can calculate again putting the value of parameters that we had and calculate the different parameters. So again we have different equations in which we have to put the different parameters like way, and again here H I will be 1, 2, 3, 4 and SZ 2.21, 11, 0.897, 0.57, 0.5. So for these conditions we have again the different parameters. We have a different equation in which we have to put the value of each parameters that we have. So again this is the equation, different equation in which we have to put the parameters we have. Again the sigma v we have already calculated in this equation, putting the value of it. So after that we will get H1 is equal to 5 and 6 and SZ is equal to 0.562 and 0.047. So this is the stata, 6 meter stata we have. In selection practical spacing of reinforcement, the designer should ensure that these are sufficient to provide the equilibrium for all potential wedge failure. So it is given in this figure. Again wedge failure we have to go for T max. We have already calculated, and this is a chart that we have prepared. The maximum value of T max is given here. We have to calculate here with the different condition. H I should be more than H minus H W. And so in this way we can calculate the T max. Again this is the chart by which we can find out the different value. So LIP we can calculate, this is 0.51, L value is already given here. So for the seismic condition again we have to go in the same fashion that we have already calculated in the static case. So we have to calculate this one, and here Z should be more than H minus SW. So we have to calculate different A3, A4, A5, A6, A7 that we have already considered in the design consideration. So this is A8, the value is already calculated 3.89. So again this is HI should be more than or equal to H minus HW. So again this is given in this table. So we have calculated 4.02. Again we have to calculate the different parameters. So T max we can calculate by this way, and this is the chart that we have and getting the different value. So here LIP will be 2.21. So L will be 5.8 times 28.7 plus 2.21. So that will come 5.38. Providing length 5 meter, required length should be 5.3, because we have already assumed for 5 meter length, but it is coming 5.38. Therefore provided 5.4 meter length of reinforcement. So thank you very much. This is the end of this lecture. Thank you.